So then let's talk about Darcy states that the flow rate through a porous medium is directly proportional to the head loss and inversely proportional to the length of flow path. And this can be written as, so we are then visiting Darcy's equation again. And he's also saying now we want to find out that permeability constant, okay? The material's ability to allow the flow. We are saying that to know that material's ability to permit the flow of water through it, it is the velocity with which this thing is traveling or the fluid is traveling is also directly proportional to the gradient, which we have discussed already. And so if I know these two things, this one we can compute from total head on L. Then I can come up with this constant which is being introduced, and we call that the coefficient of permeability. Coefficient of permeability. So I can say V is equal to this K I, and that is what is introduced there. So if I know velocity, I have velocity in mind, and I want to calculate for how much water is flowing through at a given time, the quantity of water flowing at a given time, I can multiply the area of whatever sample I am considering. So assuming it is a tube of soil, I can consider the area of the tube and then use the velocity multiplied by the velocity of flow will give me the quantity. Because if we even say M per S, you know that if we are to calculate for velocity, velocity is equal to what? Mass, meters or distance travel on per time. And so, and then I also have the area also being equal to, area is equal to meters times meter, isn't it? Length times breadth or whatever. So you also have meters square. So if I multiply meters square by this meter, I am going to have meters cubed on S. And that gives me Q. Because if I'm talking about volume, I am talking about M to the power 3, meters cubed, centimeters cubed, millimeters cubed, and whatnot. And so I can have the quantity of flow to be equal to area times velocity. And this gives me a unit of meters cubed per second. And that is why we did this multiplication here. But then we have also learned that this V here is also equal to this. So wherever I see the V, I can replace with that. And so I have A, K, I. And so it means if you have any soil sample and you want to determine the quantity of flow within a given time, you can multiply the area of that tube of soil by the permeability or the coefficient of permeability of that soil sample or rock sample you are talking about, and then the gradient, hydraulic gradient of the flow, and this gives you your Q. So then the next thing is the coefficient of permeability has the dimension of length per length time per unit time and decreases as the particle size decreases. So if I have my particle sizes decreasing, my length of flow will also decrease. But then an estimate of the actual velocity, Vs, if we have said earlier that the velocity head within the total head calculation is negligible, but there is that bit of calculation velocity there. And so if I want to check that flow of velocity through the soil sample, we give it a name and we call that seepage velocity. The rate of flow through that soil sample, although small, we call that seepage velocity. And so instead of just saying V as used earlier, we then give it a subscript S to denote seepage velocity. Good. So AV is the cross-sectional area of the pore voids. And so then, how do I compute for seepage velocity? I can calculate seepage velocity if I know my V on the porosity of the substance, then it can further be expressed like this. So all I need is know the velocity of flow times this plus that, all on E. And this is the void ratio of the soil. And then we are able to compute for the seepage velocity of any given sample. So these theories we have been able to discuss. Let's try and see if we can use that in a calculation. So it says that the rate of flow of water from a soil of cross-sectional area is this. Area 2,500 millimeters square is this. So if you remember the theories we were trying to prove, we have this as what? So I just want us to come up with the values, and that will facilitate our understanding. So what is this value here? Who can help us? Let's fetch them out. What is this one? What is this?
Look, your screen is black.
It's the internet. Oh. Is it better?
So
I think it's the internet. It's quite clear here.
Yes, it is your internet, I think.
it's okay now.
Okay. So we are saying that the rate of flow of water from a soil of cross-sectional area 2,500 millimeters square is 0.05 by 10 to the power 6 meters cubed per second. The head difference measured over a length of 300 millimeters is 60 millimeters. Determine the hydraulic gradient, which is the I, the average velocity, which is V, the seepage velocity, which is Vs, and then the hydraulic conductivity, which is K. These are the things they are asking us to compute for. And so far, the things we have discussed, you saw something like this, change in H, you saw L, and you saw something called Q. And I said the Q is talking about the quantity of flow within a given time. I said this is the total head, and this is the length through which the flow is occurring, the distance through which the flow is occurring. And then A is the area of the soil sample, assuming we are able to cut through or we filled the soil within a given area, and we are able to compute for that area through which. So let's say if the water is seeping through an entire stope face, you calculate the stope face, and that becomes your area. The distance through which the water is traveling for you to do that observation is your L. And then how much water is traveling at a given time through the stope face becomes your Q, which you need the pump to pump out. So now, the first thing for us to do here is to calculate the hydraulic gradient. So all the parameters to get hydraulic gradient, you need your length, because when I drew that figure for you, we saw this as the L, and then there was this pipe there and a shorter one at the end, and we did something like this and said this difference is the H, and that is what is measured over a length of this is that. So this H is what they have given you as 60 millimeters, and this L here is the 300 millimeters. So now that you have these values, you could easily do your calculation. So you have I, your hydraulic gradient, is equal to change in H on L is equal to 60 on 300. And that gives you a value of 0.2. Is step one clear? Then we can move on to the next step.
Yeah.
Good.
Yes.
Then the next step, it says that determine the average velocity. The average velocity. So we stated that to calculate the average velocity, we need, which is the Q, is equal to my area of whatever thing I am considering, whether it's stope face, a pipe, a circular face, or whatever, that area times the average velocity there, which is V. So if I know the average velocity, and that was given, the area was given, I know the rate of flow was given. So you see how they have twisted the question for you. Instead of giving you A and V for you to calculate quantity of flow, this time around they gave you the quantity of flow and gave you the area. So they want you to calculate velocity. So you only need to make this V the subject of the equation. And so you have V is equal to Q on A. And since this, so this is where sometimes we have issues. You have this in meters cubed per second, but then in the expression they gave you the area in millimeters square. So what do you need to do? You have to do some conversion here. So if I have millimeter square and I want to convert to, I have to divide by 1 million. So the 2,500 divided by 1 million, and that is what is here. So you have your 0.05 by 10 to the power minus 6 is equal to that. Another way could be for you to convert the meters cubed per second, change it back to millimeters. Then you can solve the problem. So you have two options. Then your answer would be millimeters per second. But I think it's ideal we go this way. So you have your final answer when you do your substitutions. Any questions? Then we can go to the next one. All right. So determine the seepage velocity. We learned that the seepage velocity, V subscript F, is equal to the average velocity on porosity, N. So if, but then we know that porosity.
No, please, we can't see your screen.
It will
It's
take
blur
time
again.
because I've transitioned to a new slide. It will take time to load at your end. All right, so I have the seepage velocity V subscript S is equal to the average velocity. So you don't mind this Z here. Every book and how they put up this in the computation and derivations we didn't use the subscript. So I just made it V on N is equal to VS. This was what we saw in the theoretical concept. So now I have this N. You realize that in the question they gave us, E is equal to 0.6. So that is where this 0.6 is coming from. And we know that E To get the porosity, porosity is equal to this. Porosity, which is N, is equal to your void ratio over 1 plus E. So you would see that I did some proving in the theory we did there, which was like this. Vs is equal to V over N. And I went further to do something like this. V times 1 plus E over E. This was what I gave. The reason is that if I have this N and I'm replacing it with this thing here, and I'm replacing it with this, it is going to be V over E over 1 plus E. And then per our basic mathematics, when you have this dividing a fraction, there is this flip. Okay, so the denominator here becomes a numerator at the end, at the top, and then this then turns to become your numerator. Okay, so you have V is times 1 plus E over E. So this is over 1, so it multiplies. So you end up getting V1 plus E over E. So this is what you would have for seepage velocity if you are to use that formula up there. So all you need to do is just go ahead and substitute the 0.6 in its place. So you have Vs is equal to your velocity you calculated. Average velocity was 2 times 10 to the power negative 5 times 1 plus 0.6 over 0.6. So those of us with calculators, let's punch and see the new numerator we will get for this. We want to ensure we have the same answers. So you get 5.3 times 10 to the power negative 5. In the same way, if you compute for only the N, you would have this, and then you now do your substitution, you come up with this. So at the end of the day, it doesn't matter which of them you are going with. Then the final thing here is for us to determine the hydraulic conductivity. So from the Darcy's law, which says that velocity, average velocity is equal to coefficient of permeability times I, which is the hydraulic gradient. We know our average velocity. So this hydraulic conductivity is the same as your coefficient of permeability, which is denoted as K. So you have this already computed for, and you know this, which you did in the first step. So substituting these things, you come up with this value. And that becomes your answer for this whole thing they have given you.